just like to say greetings to everyone from Denver, South Africa. Lovely to see people we haven't seen for months, like Esti. And congratulations on getting your master's. That was great. I think it's the fifth person in South Africa to get your CDMP master, so that's excellent work. Fantastic. So yeah, you may have heard some of the discussion we had earlier on about the work that Maria has been doing, the books that she's published, and just almost a recognition around the world in terms of what she's been working on and presenting on. And interesting, when I got the book, a lot of it came from your biology background. So I was a little, I thought you were a computer scientist. And then I saw everything was about biology and all the examples. So it was nice to see that. And I'm assuming, are you with the computer science department at the moment, Maria, or?
Yes, definitely. Yeah.
Okay, so you've crossed over onto
Yeah.
onto the bright side.
Yeah, I did after the microbiology degree, or specialized in microbiology. I did a full computer science degree and a PhD in computer science.
Oh, okay, fantastic.
Yeah. It's not even just switching and half baked, but two full degrees.
Right. Oh, fantastic. So I mean, we do see a lot of the RDF and taxonomies and that starting in the world of biology. So it's lovely to see that crossover. And certainly anyone, I know we said there'd be a discount on the books, just to be able to go through Maria's book. It does a lot of decision logic, and so things get quite interesting as you progress. I'm assuming you teach that at the university, Maria, or is this a course that you do?
Yeah, in fact, currently I'm teaching the ontology engineering course in this block. I started 2 weeks ago, and I'm teaching it until the end of August. So yeah, that includes specifically what is covered currently in the book in chapter 5.
Okay. And do you expose that to people on the outside? So can external people register for the course, or is this just for university students?
This just for university students, but I have the textbook page, and the textbook page also has the book that is for free available. It has slides there, it has exercises there, there are answers to exercises and all of that. So I'll share that one later. There's also a link there in the slides that I have to it. So that one is for free available because it's a proper textbook at the university.
Right. And I know that I've just finished a marketing analytics with Get Smart, and they seem to work a lot with UCT, and they seem to present quite a bit of the courses to the public there as well. So I don't know if that's something you're aware of.
I think people from the information systems department, a few of them do something with Get Smarter, but for the computer science department, we haven't done so far. We have very many students already.
Yeah.
So yeah, we don't really get around doing extra teaching there. That's
fantastic. Thank you very much.
We might have to think about doing so for the modeling.
Right. Maria, the last question is, would you like me to keep the questions until the end or ask you questions as you go?
We can do questions as we go along. For me, it doesn't matter. It might be nicer when people actually want to barge in and say, yeah, this specific slide, I have a question. In some cases, the question may be answered in a later slide, and then I will say so. But otherwise, I would say, interactive style would be nice.
So I'll monitor the chat and then try to interrupt it at a time where you're going to cross over on the slide. But maybe we can give Esti, because Esti always asks questions. You can ask the first question, Esti. Okay, thank you. All yours, Maria.
Thank you. Yeah. So before I start, one thing what you mentioned from the discount of the book here, I'm not sure you can see it. That one will be 20% and free shipping. I just got that confirmed from Springer, and people will receive a discount code so you can buy it there. But I asked a little bit late, and it is holiday season, the summer holiday season in Germany. So yeah, the lady who just makes those flyers was still on holiday, so it will come through in the upcoming days.
Okay, fantastic.
I hope that's still okay.
Yes.
Okay, let me share the screen. Can see the screen currently?
Yes,
okay.
We can.
Full screen?
That's it. Got it.
Okay. So yeah, welcome to the talk, and thank you again for the invitation. The topic itself that I will be covering on strengths and limitations of different types of declarative modeling languages links largely to the book that are the what and how of modeling information and knowledge. I cannot cover everything that is in the book, but there is one key component of it that actually looks at increasingly more expressive modeling languages, and we will cover that component, but only in the what and not the how, whereas the book also contains the how for that. So what we'll cover here first is some notion of introducing models, because it's also, the book was written for people who are not familiar with modeling, basically. And then we'll move on to what you hopefully already have heard of if you have done an undergraduate in computer science, is the conceptual data models. Ontologies you may not be familiar with, especially in South Africa. It is not too popular just yet. It is increasing. Somewhat you see that especially the larger companies are looking into it, but not yet the smaller ones. And the last section, we'll be looking at how do we assessing those models and comparing those models. It also will appear already throughout the presentation, but we condensing that and integrating that in the fourth section roughly, and then we'll just close with conclusions. So yeah, if you're talking about models, there are many different types of models. There are the physical models, there are mathematical models, machine learning models that most people will have heard of. You can create a data-driven spell checker, for instance, the large language models that are popular in the news. And there is a category that is conceptual models, such as concept maps. There are declarative models of mathematical models, actually. Knowledge graphs that you may have heard of as well, thesauri, UML diagrams, ontologies. There are actually a larger set even of conceptual models than listed here. I only cover a subset in the book that with which I already could make the point that I wanted to make. But it's not that these ones are the only ones around. These ones are just making the point clear. And what I will be focusing on here is a gentle, mostly non-technical introduction to conceptual models in computing. There is the odd formula there, but I hope that is not a problem. There is a diagram to go with it. So, yeah. I have several examples, and more so in the book for this presentation. And given that it is winter here in South Africa, I added a running example about rain. That we will see there. The book itself has a running example about dancing, for those people who are interested. There is somehow an increased interest from computer scientists and information technology people in dancing. There's a disproportionate percentage there in the dancing community. So, but yeah. So then, without further ado, if you're talking about the beginnings, I was assuming that especially in the English language, primary, secondary school education, people have been exposed to mind maps. In Asia specifically as well, and then for the rest in the world, it depends on where you grew up. If you have seen mind maps, and otherwise you might have come across them in industry. They are relatively well known and popular because they are easy to draw and they look pretty. So here is one very small one about rainfall made with Kogel, and basically for each line that you add, it does a different color, so you get the whole rainbow together. Basically, the colors themselves don't mean anything, but you make it just pretty visually. This is just an initial brainstorming one might imagine about rainfall, like about incidents, what rainfall does on water that goes to a pond or dam. And obviously there is a lot of runoff, that basically the water running down the hill from the rainfall. The roadside drainage is there, the stream flow that goes in Liesbeek River here in Cape Town, for instance. So that is easy to initially to draw. You just can basically put everything there on paper, what comes into your mind. However, they actually raise more questions than the answer. The first question would be what is actually a good mind map? It's the previous one that I showed. It's a small one, but is it actually good? What is the right size of the mind map? How useful is it really actually to make one? And for what purpose should we make one? How do we develop a good one? And what is actually the meaning of those connecting lines that we have? And they are actually easier to ask those questions than answers. The right size, nobody actually know. I did calculate it based on a set of existing mind maps that I calculated from what is the median and what is the mean amount of entities in a mind map, but that doesn't mean to say if that is a good size or the right size of a mind map. At some point, obviously, they would get too big and then too many things are going to sprawl and you want to break it up into smaller pieces to be able to understand it. How big that has to be, we don't know. We don't know what it is, what a good mind map means. When is it good? Usefulness. There have been meta studies analyzing studies about the usefulness of mind maps, and there have been mixed results, actually. They are largely useful or deemed useful in only some subsets of domains at primary school and the early years of secondary school. But what they largely have seen that when you go to senior years in the university, mind maps basically, they're not expressive enough. They cannot be used to cover the content, for instance, that is covered in a textbook. And that is typically something that where mind maps are being used as educational technology. And obviously the interesting part here is the meaning of those connecting lines. But I think I saw a hand up for somebody who wants to question question about the mind maps, because the next slide is going to the biological models, how we're going to fix this, at least towards fixing it.
Rizwana? You have your hand up?
Sorry, it shouldn't have been up.
Oh, okay. All right, no problem.
Okay, so
Sorry.
yeah, then continuing, so we're gonna go to first step towards a partial solution. They are those biological models that people are surprised about. What I was looking for was basically the kind of models that you see in between, from the mind maps on the one hand and the conceptual data models that you will see later on the other hand. And there are very many of those biological models. And you will have seen them and come across them in your primary, secondary school education already. So there is some familiarity with it. And then they sit nicely in between. They actually, for instance, those lines and the arrows that you see in those biological models, they actually do have a meaning. It's not just a line. There is, for the arrows, there is a begin and the end. Okay, then you can have a look at that. Let me just look at biological models, not the biological stuff that you saw in the other image that interrupted. So there are lines and arrows that have a certain meaning, but we'll see also there are icons that they're using that are typically not used in those mind maps, even though that figures could be added, but they are random figures being added or little images, whereas the icons here in the biological models, they do have a meaning, and sometimes they are structured.
Yeah, I agree.
And systematically used. And there are actually, depending on the type of biological models, written or unwritten rules on how to put them together and how to read them. So there is actually quite some systematics to that, even though that sometimes they don't look like that. So they are de facto more or less unregulated domain-specific languages. So you see here, for instance, an example that may look daunting. I think it just looks pretty. If you're used to looking at them, you see immediately things here with the CD4 card. I know. Can you see my mouse?
Yes, we can.
Okay, good. So you see a CD4 and CD8 counts that may the name CD4 and CD8 may be familiar from HIV, for instance. They are similar cells, so they have similar notation, even though they are different, so you can visually see what they are. So they are elements, and the writing underneath is just for people who are not familiar with the notation. And you see here, for instance, the Golgi apparatus, mitochondria, they are specific elements there. No matter which biological model at the cell level you're looking at, they always have the same kind of notation. So it is not that this Ostaszewski's and co-authors have been drawing this manually themselves. This is actually designed and developed with existing software that has those kind of stock images already. So basically, actually, in a way, a domain-specific language with specific elements that you can drag and drop on the screen, on the canvas itself. The arrows here have specific meanings as well. For instance, here you see antibody production, and you see when here an antibody, the same element there, that means that this element is actually moving there. So that is a meaning of an arrow implicitly there. As you're learning along about microbiology or cell biology, you learn that kind of notation, you learn how to read it. So there is actually, in that sense, a structure and a systematics to it. You see also here the different boxes where you say, well, this is a cell, this is a specific compartment where things happen. So I'm not asking you further to analyze it. I'm just highlighting a few components because they are recurring components in those biological models. Here is something at the other end of the scale, for instance, in ecology. When you look at, again, rain and runoff generation. So I got a running example. You could see that here for the different elements, you have arrows again. And for me, when I look at that, the other thing, if I put my hat on of computer scientist, I see a graph. So for instance, as you have here an overlay, you have your rainwater, you have your overland flow, and it goes into a stream. So you actually have elements and relations between them. So even though that those diagrams may look unfamiliar, especially to somebody with an IT background, they actually have an underlying components of graphs and nodes and edges and things going into different directions. Yeah. So
I've just muted them now.
Yeah, thank you. So that is one component of when you look at the diagrams, and this notion of a graph, we can do the same thing as maybe as in the previous figure. So there is a structure actually underlying those diagrams that some people would have called cartoons, but they actually are systematic diagrams for that. Also, if you look at the mathematical models and you take the annotations of mathematical models, when I show this to the hydrologist, if I look, here is your mathematical formula, where we can annotate this in a biological diagram, hydrological model. You see your rainfall, you take a stock image there, ponding loss, you take a stock image there. And they were happy with this diagram for that when I showed them that. And they think, well, yes, this is clear. There are, however, limitations of those domain models, because even those two that I already showed you, and they are real models from existing documentation, there are actually very many notations to learn. There are those objects and arrows, but there's no way to specify how many outgoing arcs there are, how many of one object relate to another object, for instance. With those very many notations to learn, it also means there is a proliferation of incompatible modeling tools that are cumbersome to maintain, because you have a whole cottage industry of different modeling notations. And they are diagrams and they are static diagrams that give limited computational use amongst the models. if you see those diagrams, there are so many more things you would be able to computationally do if only you had a computational representation of it. You could see which models are the same, which one overlap. You can put models together, for instance, and you would be able to do such a computational analysis that with just a static diagram, you actually cannot do. So as a last slide for the introducing the models, if we apply that again to these loose ends in the model for the running example about rain, what are the names of the relations? What are the constraints that hold them? What are the relevant attributes? Should you record anything about the data types? All of that is not mentioned here in the diagram, and there are still questions that are actually remaining. So that we can solve in a way with our conceptual models. I thought I saw a hand up.
There was a question from Esty, and it was on the biology models, in terms of who decided the notation for, to get an agreement of that notation, and how it was working.
For this one, there is no agreement. For this one, this specific diagram, it's the software developers who made this tool that help you to draw these diagrams that decide on the notation. There are other notations, especially for chemistry models, the diagrams, the chemical formulas. There is an international association, and that international association decides this is how it has to look like. Okay. For some other diagrams, for instance, for the evolutionary trees, it's the scientists who decided this is how it has to look like. And this is a good model and this is a bad model. So if you make a mistake in a notation, that then actually amounts to making a mistake in understanding the scientific theory behind it. So sometimes it's the scientists who agree informally, other times you have an organization of the scientists in that specific discipline who set the standard, basically, and who decide how you draw those things. And then other people, they jump on the bandwagon because it makes it easier to communicate because other people are already familiar with a particular notation. So yeah, there is no single answer to that. It's generally a community who agrees on the notation. So yeah, for that, the more or less agreement, but still in a way, having these kind of limitations of the domain models, even with the agreement that the domain specialists have, there are still those issues with those kind of models. So the solution to that, with those limitations for those domain models, would be to devise actually one notation for all subject domains that is a little bit more expressive, or basically with more features than arrows, to have that computational support that we really would want to have, to be able to analyze those models better. And indeed trying to standardize that to make the tooling development essentially economically viable. Because then you actually can develop a tool and maintain it because there are more people who actually take up that specific tooling. And then we get to our conceptual data models specifically that we use in IT. So with the conceptual data models, not just conceptual models, that is a larger basket of different types of models, is for a class of models that capture the information about the data that are to be stored in the prospective software system and possibly manipulated, assuming you want to manipulate it. There are, however, several conceptual data modeling language families and notations, but they all are based on the same principle. So I'm showing here a few notations to give you an idea of the different notion of notations. However, what they all have in common as conceptual data modeling languages, there are things like what you see here, entity type. You have something with an identification or an identifier attribute, one or more. There are attributes of a specific entity type. you relate entity types through relations that can be named and actually have constraints of mandatory or optional participation. One participates, maybe more than one participating. And that can then hold across the different universes of discourses or whatever you want to model specifically. So to see here an example for those ones who are not too familiar with the conceptual data modeling, in the crow's feet annotation, you see, for instance, here, for book and author, there's a right. They relate to each other through a wide writing instance, obviously also through reading, but let's just assume here for the writing, you have the many side here. So you have one book relates to multiple authors, possibly, and one author relates to multiple books, and you have this nice crow feet that you have one to many outgoing, basically. And the option, that is the mandatory, that must be the case, and here this round one means optional. So you have a book with an editing relation to the book editor. How that looks then with population examples, if you link that specific to the data, to the instance level, and so you have a type level on the left-hand side and the instance level on the right-hand side. That you see, for instance, that it, Carrie, and the talisman, all three of them are written by the author Stephen King. But you also see that Stephen King and Peter Straub actually wrote the talisman. So you have basically a many-to-many relation there. Optional in this case means, for instance, between the books and the editors, that some book may not have an editor, and then some editor may not relate yet to a book. The one thing is with those conceptual models, because they have the same foundations, we can swap between the different modeling languages, between EER, UML, and class diagrams is another category. Object role modeling is a third category. So if we look at if we now compare, for instance, the expressive example of the talk's announcement and the start of the slides that Debbie showed, as well compared to, for instance, the software design. If you have just your simple lines here, you can actually see there are three different kinds of relations for in more detail. For instance, an espresso machine accepts coffee input. There's a part whole relation that is drip trace stream mount and the button are part of the espresso machine. The dose button and power button are standing in an ISA relation to buttons. So, yeah.
Sorry, Maria, there is a hand up. I believe it's from Trent. Trent?
Oh, I'm sorry, it was a mistake. I'm sorry.
Okay, all right. Okay.
So if we think about our rainfall, if we would do that in UML style, what I did there for the hydrologist as well, you see here an example. And the UML style, you have your class rainfall, your ponding loss, your runoff. You can convert it into semi-automatically into program code because we can have a soft copy version of it. Easier to communicate with other domain experts and easier to reuse with those other mathematics formula because they use the same entities. So when I showed them this, the fact that we had names there and the fact that we had multiplicity constraint, they were pointing it out from, yeah, no, actually with runoff, we mean runoff measurements, not just runoff. And there may be different systems when we're trying to measure the runoff for specific rainfall events. And there may be different systems. Some take measurements only every 1 hour, some only once at a time, and there are different ways of measuring. So there has to be a measuring time really as well. And just for the fact to have more and more features that we can use to represent more, it actually came about from, no, actually we have to have this kind of data in our system too, which a specific biological model or those informal diagrams wouldn't do because you're not required to actually think about it. The thing, however, with those conceptual data models, they are for one specific application only, and you need to redo it for each application, which can generate integration issues. So if they have two systems in different places where they need to record the data, then the model would possibly could clash. The other thing is that if you develop your model in isolation, you have to reinvent certain modeling solutions that in the meantime, over the years, we actually already have figured out. And we don't want to reinvent the wheel, or we don't want to make the same mistakes either. You want to have learned from the previous years and the previous experiences so that your model instantly already can be better, which we currently cannot do with just conceptual models. Still, also, they are mostly informal diagrams. Derogatorily, sometimes they're called boxology. They suffer from ambiguity, and that maybe intentionally or not. Sometimes the modeler itself, him or herself, doesn't know, and then he kicks the can down the road, and the implementer has to figure out what they're going to do with it. Only limited authoring guidelines, which, however, is more than with the mind maps and the biological models, but it's still only limited for what you're going to have to do. There are at least some quality control mechanisms that are largely absent from the other two types of models. Which brings me to the last category, that are ontologies. We're solving there with the limitations of conceptual data models. Basically, we have a model for a specific subject domain rather than a single application. There's of use across, and you use that across the multiple applications for use, reuse, and integration. They also provide solutions to recurring modeling issues, so it saves you reinventing the wheel. They have it logic-based, so that it's as precise as permitted within the language. And we have multiple quality control mechanisms, theories, methods, techniques, and tools for that in our toolbox. So informally, an ontology is an engineering artifact in machine processable format, which contains the entity types, their relationships, and constraints that hold over them for a particular subject domain. So on the right-hand side, you see a very informal diagram of the gene ontology. There is a formalization behind it. But you can see here, it's a directed acyclic graph for it. There's also the most popular ontology, and they started develop it in 1998, and it has been growing and growing to thousands and thousands of entity types, and has been used across very many applications and scientific papers for it. If you were to design your ontology yourself, or you see in a specific ontology file and you want to open it, typically you would do first, they open it in something like Protege, and you see, for instance, here a graphical notation in the graphical interface of a specific text file, because your ontology at the end is a text file that looks nicer in the interface with different places where you have the information, like a lion is an animal. You see that here on the right-hand side as well. Eats only herbivores and eats at least one impala. That is on the interface. Behind it, we have our text file, and that is really something you can open in notepads. So yeah, you see a subclass of lion is an animal. It's the same notation as you see a lion as a subclass of animal. Behind that notation, we actually have our logic. The textual notation is really a textual rendering of things that you see here with the symbols, the subclass notation, the for all, and the exist. Behind that logic, and this is a specific notation for description logics that we use for ontologies. Description logics themselves are a fragment of first order logic. So this is a first order logic rendering of this little bit that you see here, that's the lion subclass of, and these three axioms in there. Now you may want to wonder, why would you want to do all of this effort in the modeling? We do get something back for all that effort. That is one thing, is automated reasoning. The automated reasoning helps us to what you sometimes people would call debug an ontology. So improve on the quality of our ontology, as well as finding implicit information you hadn't realized yet. So for instance, I have here this set of axioms here at the bottom. You see B, C, and D are all A's, which you have here as well. So B is an A, C is an A, and D is an A, is similar to like ER-ish like notation, abusive notation, to be honest. B is related to E, and D is the same way related to E. You say you see B, there's at least one R relation to E. You see that for D as well, but it has another property, and that is there exists FC, as an S relation to F. Running the automated reasoner, it will find out that our class D necessarily must be a subclass of B. We get this for free. So this one notation on the left-hand side, it wasn't wrong what you had been drawing there, what you had been formalizing, but this is really what you have logically and ontologically. So that is something you get for free. And this is maybe for a small model easy to see, but if you have thousands of those classes in there, the automated reasoning really can help with that. How it is being used, or initially where this would be used in applications, originally envisioned in the 90s, was that our ontology for that specific subject domain was sitting on top of those conceptual models that we saw in the previous section. Because those conceptual models, we had different models for different applications. What you see as well, database with a model, another database model, maybe an object-oriented application, C++, Java, whichever, had their own model. To be able to integrate that, instead of making mutual relations between those conceptual models, we have that ontology sitting there on top, providing the common vocabulary and constraints that hold across the applications, and then making a link and basically saying, when we talk about a flower in this database, we talk about this kind of thing. When we say in the ontology, we have that here, for instance, in Dutch database Bloom, there's also flower. We link that also to flower, so then we know that both databases talk about the same thing, to actually really to provide that, then the ontology in that sense provide a glue in the data integration. And you can do that if it is subject domain specific, but application independent. Whereas these ones for the conceptual data models, they are application dependent typically. So why do we do that? One, for the data integration as the original motivation, for their own sake, maybe as well, for possible future use. Back then, 20 years ago, currently, no, everybody agrees there has to be a purpose to it. Even if it could be just representing a scientific theory precisely, because it gives you the mechanisms to be precise. When you're modeling in such detail, it facilitates communication among humans to see, okay, did you actually agree, did you disagree on a specific component of your theory? And it can be between software applications, but since applications have become largely more complex, and you can a system with many subcomponents, you can use the ontology to glue the subcomponents together. So for instance, the Watson, IBM Watson uses several ontologies to put the different modules together to make the whole system there. And it's used in many different ontology information-driven information systems in the meantime. Not just a data integration, but also recommender systems, NLP, textbook enhancement. I have a couple of examples here that I can share later. Saving research time, energy optimized building systems control, digital humanities, you name it. They're using ontologies for various things that originally had not been foreseen. So what we have then at the end now, these days, is actually a much larger orchestration. We still have here, you see in the little corner there at the bottom, our databases and application, the conceptual models that it relates to. It reuses elements from the ontology here, from the domain ontology, or basically it extracted to help developing the conceptual data model that we still have, or we had an existing one and you link it up there. What we see as well, for instance, in an ontology-based data access system, they use components and aspects of the ontology directly for conceptual-based queries for that. And there are other tools, for instance, intelligent textbook, annotating text, automatically generating questions, automatically marking those questions for that. Plus that we have different modules within the ontology itself. So we have a top level components, we have domain level components that we link to more get a bigger network of components for the ontology. So if you think back at our running example about rain and rainfall, here is a sample sketch, some axioms for an ontology, a bit more precise. What you see here, the logic-based representation and a automatically generated natural language rendering of the elements. So when they showed these axioms to the hydrologists, they were like, yes, but this specific thing, the rainfall causes runoff. I said, okay, that must cause runoff. And so they were like, no. If you have to be this specific, no, it's not the case that rainfall necessarily causes runoff, because the rain may just go into the soil, and the soil may absorb all the rainfall. So that we could specify specifically. Another thing that we give us the conceptual tools, so to speak, to analyze it. For instance, when we talk about rainfall, are we talking about the event, the rainfall, a shower that is taking place, or are we talking about the amount of water that actually has been falling down as the notion of rainfall? And they are two different kind of things. One is an event, the other one is an amount of matter. Your ontology will help you clarifying what you really are talking about, that the conceptual data model may not easily do. Are there limitations of ontologies? Yes, there are, but that is not part of this talk, because otherwise it would take a long time. What is beyond ontologies, if you think this is not enough? There is ontology with a capital O, which is a branch of philosophy that investigates the nature of things, on paper mostly, and that looks at what is part, how it's causality, what's the notion of a function, what is amount of matter, for instance. So they will, in that sense, help a little bit with the ontology development, and can inform some of the conceptual data modeling. But in the interest of time, I will continue to assessing models themselves. If there are no questions, I don't know if maybe all of this ontology was too much of a good thing and you like conceptual data models, or maybe you're excited, or maybe you have a question about ontologies. Before I'm going to...
Let me ask, is there anyone who has a question? If you can put your hand up. I don't see any questions. Not a question. I think someone has asked, seeing the crosswalk of logic statements to Protege was very helpful. It's been hard for me to decipher the logic syntax before. Mm-hmm. So I think she... Leah, is there a further question?
This is Leah. Just wanted to, can you hear me okay, first of all?
Mm-hmm.
Yes, we can.
Okay, great. No, just thank you for the talk. Yeah, seeing this crosswalks, I've done, I think, to those statements before and just like glossed over and like tried to like run through it. But seeing the crosswalk between the statements and Protege and then the statements and the logic statements was very clear. And I could like, oh, that all makes sense now. So just wanted to praise that. I guess there is one question I have, and you talked about some of the UML and some mind maps. I was wondering if you've ever thought about how logic models fit in this. I have a lot of colleagues who love logic models. They're more in the like they're social science methodologists, that kind of thing, and I wasn't sure if logic models, if it's just a variation of maybe some of the things that you've discussed, or if it's something different altogether.
I'm not 100% sure what you mean with logic models. I know there are several things called logic models. I'm not sure which one you're referring to. The one that I instantly think of is the logical layer for databases with your relational algebra. I'm not sure you're referring to that one.
No. So the best way to describe it is there, I guess, visually a bunch of rectangles that kind of list out and talk about elements of a thing. So I guess with your rainfall example, instead of showing maybe the kind of a draft by map or some of the visual display of a mountaintop and how it all works together, there would be like maybe let's see, a rectangle for rainfall and a rectangle for after the rainfall and a rectangle for environment of mountain and another, you know, and there would be connections in between them.
Yeah,
so
okay.
it's kind of like a human readable UML model, but not, that's the best way I can describe it.
So there are some of those ones. One is the frame-based semantics that has notations like that. For some of them, there are also various graphical representations of the ontologies that we have, and various graphical representation of the first order logic modeling to visualize it for the non-logicians, basically, which is like 99% in the world, or 99.99% maybe even. So the one thing with the diagram notation, what we have seen when we try to visualize all of this aspects of the logic, is that certain things we could not manage to draw, basically. And there are more features that are available in the ontology languages that we have than we are able to model. So maybe your logic models will work, but only for basic constraints. And then there's the same thing if we look at what is the expressiveness, what we have in the conceptual data models, what can we do in the logic? In the logic, we can say more in the end. Well, not all logics, but the first order logics, at least. So yeah, there is a difference there, and some from the computer science perspective, we see the diagram notation largely as syntactic sugar. To help interact with the end user. We have that with the natural language generation as well. There are several controlled natural languages that are a fragment of natural language or pseudo-natural language that has a mapping with the axioms that we have. And there are various notations for that.
That's helpful. I like the synaptic sugar description, because I did pull up what it actually means in my context. So it talks about a situation, inputs, outputs, outcomes and impact, and then assumptions and external factors. So it's kind of, but they're kind of laid out in rectangles and like a chart form versus any more and there are some arrows in between of things, but yeah, it's very much bulleted list in these rectangles with arrows in between. So synaptic sugar, I think I'm going to take that away too. Thank you so much.
Yeah,
and,
it's okay.
I'm from just outside DC, so thank you so much for posting this to your LinkedIn.
Yeah, thank you for attending. It must still be early in your time zone. Yeah. So there are definitely other conceptual models. There are also process models, and what you're talking about is might also be closer to process models than the conceptual data models. Okay, so let's continue. Sorry about that. Wasn't me either. We just look, continue with our more different kind of models. Models for computation, models for conceptual models. So there are definitely, to come back to Leia's comments, for her logic models, there are definitely also others like the process models that are around there. There are also other domain-specific languages. But here I was looking at the declarative components for the models, to basically look at, okay, there are different ones, and we're starting easy, and then you think that is okay, but no, actually exposing people to the limitations, and we went from mind maps all the way to ontologies. What, however, is also the case, and if you compare those ones on a set of features, we can do a feature-based comparison as well as task-based comparison. Feature-based comparison here first is, if you're looking at the main aim or function, our mind maps will not be able to solve that because they only there as a main aim for basic structuring of a topic. So the precision is then also low because it doesn't matter you want to draw something quickly. Whereas if you want to analyze a domain for data integration, you need to have high precision and typically also the language freedom and high expressiveness of representing those details, so that you know what is the same and what can you integrate and what is different, what you cannot integrate in for the different systems that you want to put together. So actually, so then we see there are different aims and functions of the different models. They are used in different realms. For instance, typically mind maps are popular in education, technologies, and businesses, which is something for ontologies. It's basically the back-end technology. It is a facilitating thing at the back end to make an intelligent system, to make an ontology-driven information system, which mind maps are not intended for. They are not intended for the computation. So there are differences there on different purposes. If we look at, so I'm mindful of the time here, task-based comparison. If I would ask you about the different models about rainfall that we have seen, which model would you think is the most useful, and for what? And what makes you think from, yes, this is the right level of expressiveness, the right level of detail? I don't know if somebody would want to, has an opinion about that already, or maybe not. Okay. So in the book for a specific task-based comparison, that mind maps are generally claimed to be great for learning a textbook. So I took a textbook page and basically tried to make a model in each of the different types. And this case was about labor relations. What actually came out of that was the conceptual data model was a winner as a best trade-off between ease of modeling and the expressiveness that you need, because that about the labor relation was an undergraduate or postgraduate textbook, so you need to have that kind of detail. Except unless if critical inquiry is the aim, basically. There's a higher up in the Bloom taxonomy. The Bloom taxonomy basically starts at the bottom with, can you reproduce the information? There are different layers about, and all the way up, can you create something new? And can you, and below that, the analysis of a specific subject domain. If that is not needed, then for learning textbook content, you would not need an ontology or to develop an ontology. Then you deal with your conceptual data modeling as ideal. I know people also have asked me about model quality. So I'll mention here a few things only. That for model quality, in principle, what we can do if we look at assessing models, not only comparing them against each other, but also on their own. Syntax stacking is technically straightforward to implement, even though not all the tools do. The thing, however, each type of models that we have seen, what is a good model, can be answered only partially. And typically only one aspect at a time, because scientific experiments with humans are limited in the way that they have been carried out and hard to do because we have few humans to do it, and there are very many factors that can affect it, and it's very hard to control for that. The other thing is, for helping with model quality, the most theories and methods and techniques are available only for ontologies, and only some of those have been ported back to conceptual data models or biological models, not that is still a tabula rasa to improve on that. Some things we don't know yet how to check for, and that is one thing for a last comment here. And that is basically, if you have built bias into your models and into your representation, and what would it mean when you build bias into it? It's a problem. We know it's a problem in data-driven AI technologies, and then you could wonder, do we have that with our declarative models and conceptual data models, ontologies? Do we have that there too? Is it the same amount of problem? I would say no, but it also doesn't mean it's necessarily free of those kind of biases. It's currently, however, not part of modeling guidelines, methods, and methodologies, but maybe it should be. Where bias could occur if when you do the manual modeling, it's mainly a conscious modeling decision during the modeling process, so should not be an unconscious bias because you're actively modeling there, unless you try to come up with automated methods to create one of those models. So where did it happen? Where could it slip in? Here's one last slide on that, from where could candidates, or where it may come from, or when you're modeling, to think about when you're modeling, oh, am I not falling into this specific trap? Property manipulations. That is basically which properties and which attributes to record or to put in your model, which one to exclude. For instance, the calculations about whether you need to, for the air conditioning and heating, what amount of air conditioning and heating do you need? In the European computations include things from do you have equipment in a room? Do you have insulation? Do you the ceiling height? The United States, for estimates, do not do so. To what extent does it actually have an effect on the things that those systems propose that you need for a strength for air conditioning and heating? The other thing, what is well known, is setting the permissible value ranges. For instance, for hypertension, if your system says the hypertension, so like if the normal range is smaller than it used to be, that means that more people up here and down there, so up here, have hypertension, which then would qualify more easily for medicines, which is good for the pharmacological industry, but not so good for the insurers. There's also an existing example on the alcohol use disorder had been redefined, and instantly loads of more people were diagnosed with it, or would be diagnosed with it, purely by model, varying the values that we had in the model. Other typical example is aggregation or granularity. How refined do you model something? And terrorism databases, they are multiple ones are around because everybody wants to build in their bias. For instance, if you're going to record bombing targets, you're going to say just government building, or you're going to make subclasses for a different kind of buildings. Because if you can do so, then you can distinguish between, clean bombing or there's not really clean bombing, but not bombing, not civilian things, or what some people were consider the dirty bombs and the clean bombing. Whereas if you have only the government building, then you cannot make that distinction. Maybe you don't want to make that distinction because you have you invested in one side of the conflict rather than in another side of the conflict, and those things they do happen. Other issue, familiarity bias. Putting one's cultural narrow assumptions in the database. Optimism, pessimism bias is another one. That there was a subclass of where the COVID drug in clinical trial is a COVID drug, which is obviously not the case because it's not been approved to that, but they was just hoping it would be. So then, concluding the presentation, unless somebody first still has a question or comment on the bias.
Maybe just to ask everybody, has anyone got a question on that for Maria before we go on? No questions.
Okay. So then what we have seen in a very, very brief span of time, I know I crammed it with lots of information. We have seen different types of declarative models, specifically mind maps, diagrams, typically from biology, an example from hydrology, conceptual data models, and ontologies. And modeling languages with expressiveness, strengths, and weaknesses. Which one suits best essentially depends on the task at hand. If you have to brainstorm about, I don't know, a flooding that is currently going on, you should not develop an ontology, basically, because developing an ontology, you have to sit down and think a model, and you don't have time for that when it's flooding, and you need to have instant solutions for that.
Yeah.
So that gets us into interaction in a way with professionalism in modeling. You need to know which type to use when, basically, to actually do responsible modeling in that regards. Other thing to if you were wondering, does it make sense to model? There is actually a resurgence in interest in modeling, thanks to, or maybe due to the limitations, whichever your perspective it is. But when you have only data-driven AI, they see that it's not enough to only statistical-based and machine learning-based approaches. They want to infuse it with knowledge, and then you get, for instance, neurosymbolic approaches that need some of these kind of models that are manually curated, where the knowledge is basically properly represented for it to merge that or to enhance one with the other, and it can go both ways, basically. There are, however, also still plenty of opportunities for developing tools, methods, methodologies, quality control, evaluation, bottom-up development from diagrams to the big models, and so on and so forth. So there's plenty to do still for that one as well, for interests for that. So for that, to last comment, the acknowledgements, they're also in the textbook and funding sources, and as I mentioned, Springer for a 20% discount on the book. The discount code will be probably communicated later today or tomorrow for that. And thank you. There was the link to the book. If you can't get enough about the ontologies, there is that free book here with free exercises online and slides as well. That is here on my website. The other people's OE book. It's also available in paperback. I'm making a new version of it for probable release in 2025 to update it with the latest of the latest. So that's it from my side. Thank you.
Thank you. Thank you, Maria. Thank you very much. I'd just like to apologize to everyone for all of that stuff that's happened. I'm still a bit shaken. But I have one question. Lots of people are talking about ensuring the quality of things like OpenAI, ChatGPT by using the ontology to constrain what goes in terms of prompting, and then also when it comes back out again, it will be validated against an ontology to see whether it's hallucinated or whatever it is. Is that sort of what you mean by data-driven AI? It's all, there's no guidance like an ontology that guides it. It's just finding connections.
Yeah, so the basic LLMs, they are just data-driven. You just put the text in and analyzes it with neurological models, the deep learning. So there's a set of algorithms for that. They analyze it and they structure it. The statistics base are the basic ones that they initially started with. But there is, in that sense, they are not trained with a certain knowledge about reality, for instance.
Right.
And you would want to have this notion of a grounding and just look what is the most probable to match, to be similar. But that doesn't mean that it is actually semantically matching.
Okay.
And the ontologies, or even already knowledge graphs, they will help in some way that they can guide either the search or in some cases they talk about retrieval augmented generation.
Right.
That you put your knowledge graph or your ontology in there to help with that, basically.
Yeah. So it improves
so it improves the output. You can check it against the knowledge graph to see if it's correct. You can do fine-tuning of the LLM with an ontology to get better output as well in a specific domain. There are various ways of combining the two. That would be a separate talk, but there are possibilities to enhance that.
Thank you.
And that is also with, for instance, the big data and the big data analytics. They also use knowledge graph, and since the 2000s that they already been trying to mix it with ontologies, both to help finding clusters of information in the data, as well as seeding the clustering and matching the two, basically, of the data and the classes in the ontology.
Great.
No.
Thank you. Any other questions? Mr. Grubler, any questions from you? Like it. Anybody have another question? Doesn't look like it. Maria, I'd just like to say thank you. Thank you so much. And apologies again to everybody for what's happened today. We'll certainly try to resolve that. But I appreciate what you've shared with us and everything that you've brought to the table. Thank you.
Thank you.
Thanks, Marianne.
Thank you
Okay.
so much. Have a lovely evening.
Thank you so much.
Thank you. Lots of food for thought.
Thank you. Thank you.